Yeah, go on.
Ready? Okay. Welcome, DataOps. Meetups, Magnus Lovisa, stage is yours. I'm stop sharing. Magnus, your turn.
Thank you so much. An impressive line of meetups. Okay, if you're asking yourself if Apache Kafka is better than RabbitMQ or if RabbitMQ is more reliable than Kafka, I want to stop you right there. We have seen many articles and interviews where Kafka shine in front of RabbitMQ and others that do the opposite. And a lot of us could plead guilty to listen to the hype and running with the crowd. And therefore, we feel it's important to know that the decision of whether to go with RabbitMQ, Kafka, Pulsar, or other solutions is dependent on the requirements of your project. And a true comparison can only be made if you use them both with the correct setup in a fitting scenario, where you have knowledge of available features or plugins. And since comparisons between these two brokers are often made by assuming that they are essentially the same and are supposed to solve the same issue, we are here today to give a different perspective and show the differences between them. And by that, we mean showing what makes one or the other more suitable for certain tasks. So we can go to the next slide. Thank you. My name is Lovisa, and I'm working at the largest hosting provider of RabbitMQ, namely CloudAMQP.
And my name is Magnus, and I work as a developer on CloudAMQP and also on Cloud Kafka. Besides developing new features, I also work with customer support for both these products.
Yeah, and 84 Codes, the logo, is the company behind these two products. And among other services, we have some software as a services for databases and the Internet of Things as well. And for all our products, we offer fully managed clusters that are easy to monitor, and also we offer around-the-clock support. And we therefore feel confident to talk about this subject during this meetup today. And we have seen many good and also some bad use cases for both RabbitMQ and Kafka. So we will start to talk about message queuing and RabbitMQ, followed by an introduction to Kafka. And here we have tried to highlight the differences that we see in them and describe them, meaning that we might describe the option to prioritize messages in RabbitMQ or streaming or routing, but not talk much about asynchronous communication. And this will hopefully make it easier for you that has only been working with one of the softwares to follow along. We will then compare them from a more extensive perspective and show main use cases for both of them. So what is RabbitMQ and message queuing? Let's start with the basic architecture of a message queue. We have producers that create messages and publish them to the message queue. Then the receiving application, called a consumer, connects and consumes batches of messages from this queue. A message is the data that is being transported between a sender application and a receiver application, and it can contain almost any kind of information, such as a signal that informs an application to start processing a task, or it could simply be a text message. Our own architecture at 84 Codes relies heavily on RabbitMQ, and I will give just one example of how we are using message queues. We have, as I mentioned, a database as a service offering, and for that service, we perform daily backups on all the databases. And now I'm talking about thousands of databases. And this is, of course, an intense process and takes time, especially for some of the huge databases. And that's one of the reasons of why we added a message queue between the service that requests the backups and the one that actually creates the backups. So here the producer sent thousands of create backup messages to the queue. And the create backup messages stay in the queue in the same order as they entered the queue. The application that creates the backup then consumes the message and handles the request. And here we also have an option for customers to create backups on demand through a customer API or through the web interface. And if a customer creates a backup on demand, this backup should of course be available for the customer immediately after the request was sent. In other words, this specific backup should be a priority. Luckily, RabbitMQ has a priority queue implementation that can be used in this scenario. The create backup message is added to the same queue as all other messages, just with a higher message priority than all other requests. There are two possible ways for consumers to acknowledge message delivery back to the broker. One or more messages can be acknowledged once they have been sent from the broker, which is called an automatic acknowledgement. Otherwise, a consumer can manually send back an acknowledgement when the consumer has completed the task. It's also possible in RabbitMQ to NAK a message, sending a negative acknowledgement. And this can be done when the consumer wants to tell RabbitMQ that the message was not handled as expected. And by doing that, the message is added back to the queue. And such a message can be resent or discarded after a number of retries. A message in RabbitMQ is removed from the queue once it's acted by the consumer. RabbitMQ also gives you the option to set a time to live, TTL, for both messages and queues. A message that has been in the queue for a longer time than the configured TTL is said to be dead and thereby removed from the queue. And messages that are dead or for some other reason dropped from the queue can be republished to another queue and thereby handled again. RabbitMQ also supports delayed scheduled messages. With a plugin enabled, a producer can send a message to RabbitMQ, and this message can be delayed a given time in RabbitMQ before this message is routed to the consumer's queue. RabbitMQ is a message broker that allows clients, producers, and consumers to connect over a range of different open and standardized protocols where AMQP is the default one. And AMQP include a lot of standards that RabbitMQ has included into the broker along with other extensions. And one of these things are routing of messages via exchanges. And you can think of an exchange as a mail delivery person, ensuring that the message ends up in the correct queue. How a message is routed depends on several things, including the exchange type, which specifies a number of routing rules, routing keys, and header attributes. And these all act as addresses for messages. And from the queue's perspective, you can check which exchanges and routing rules are linked to this specific queue, and these links are called bindings. A binding links the queue to an exchange, while the routing key is like an address for the message. And this is mainly what the exchange looks for when deciding how to route the message to queues. And RabbitMQ has 4 main types of exchanges, and we'll describe them a little bit. The direct exchange directs the message to a specific queue by looking at the routing key. And the routing key in the message is compared for equality with routing keys on the bindings, and they are also sometimes called binding keys. We will use an example from a taxi company to explain the different exchange types. Every request for a taxi is made through an app that communicates with an application service that uses RabbitMQ. So in our example, the direct exchange is used when a user requests a specific taxi, like their favorite driver. And we can see here that we have two cars that are bounded to the exchange, and that the message goes from the exchange to taxi A in this case, which is the favorite driver. Topic exchange routes messages to one or many queues by looking at a routing key. And the routing key in the message is compared for matches with routing key patterns on the bindings. In our example, a customer with a group of friends asked for a large and environmentally friendly taxi. And this order is routed through an exchange bound only to taxis of this type. And here we can see that if we go back, we can see that the message is only sent to the large and eco-friendly taxi D. Okay, next. The fan-out exchange copies and routes a received message to all queues that are bound to it, regardless of the routing key or the routing keys. A provided routing key is simply ignored. And in our example, the fan-out exchange is used when the taxi coordinators inform all taxi drivers about a blocked road. Finally, the headers exchange. They are very similar to topic exchanges, but this one routes messages based on header values instead of routing keys, and this exchange is not often used. Okay, let's leave the routing and talk a bit about clustering and scaling in RabbitMQ. A RabbitMQ cluster is a logical grouping of one or several nodes, each sharing users, vhost, queues, exchanges, etc. And a single node cluster usually give better performance than a multi-node cluster because no data need to be shared between these nodes. On the bad side, if this node or server goes down, RabbitMQ is down, and we at CloudMQP have, of course, added monitoring tools that automatically detects the status of all nodes in the system. So all RabbitMQ brokers start out as running on a single node, and these nodes can be joined into clusters. And since RabbitMQ version 3.8, RabbitMQ has something called quorum queues, which has consensus-driven leader election and replication. And it's a big step up from the classic queue mirroring technique that RabbitMQ used to rely on for replication before version 3.8. And this means that the majority of replicas, including the currently elected queue master, agree on the state of the queue and its contents. Certain failure scenarios can result in mirrored queues confirming messages too early, potentially resulting in a message loss. But a message sent to a quorum queue that is successfully confirmed back to the publisher should not be lost, as long as at least a majority of RabbitMQ nodes hosting the quorum queue are not permanently made unavailable. We at CloudMQP are trying to encourage our customers to get familiar with quorum queues, as well as the RabbitMQ core team. We try to make them consider quorum queues instead of classic mirrored queues for a lot of use cases. And quorum queues are both safer and achieve higher throughput than mirrored queues. There is one other queue type worth mentioning, and it's lazy queues. And the main goal of lazy queues is to be able to support very long queues, which can happen when consumers are offline or are down for maintenance, or when there's a sudden message spike, etc. By default, queues keep an in-memory cache of messages and to be able to deliver messages to consumers as fast as possible. So whenever the broker needs to free up memory, messages from this cache will be paged out to disk. And this process takes time and blocks the queue, making it unable to receive new messages while it's paging. Lazy queues write messages to disk immediately, so spreading the work out over time instead of taking the risk of a performance hit somewhere down the road. So messages are only loaded into memory when they are needed. Quorum queues store their content on disk as well as in memory, so the lazy mode does not apply to them. That was a quick intro to RabbitMQ and some basics in RabbitMQ. Magnus, do you want to talk a little bit about Kafka?
Yes, let's talk about Kafka. Apache Kafka is a messaging system that allows records to be sent between applications. Kafka is mostly known for its high throughput and low latency. There are 4 parts in the Kafka system. We have the broker. There can be 1 or more brokers in the cluster. And it handles all the requests from clients, produce, consume, metadata requests, etc. It also keeps the data replicated within the cluster. Then we have Zookeeper. Zookeeper basically keeps the state of the cluster to know which brokers, which topics and users there are. And then we have the producers and the consumers. We'll start to look at the producers and then consumers. There might be some terminology on those slides that are new to you, but I'll try to cover them afterwards. Otherwise, you can save them as questions for later. Message in Kafka looks like this. They have a key, a value, and then they have optional fields like timestamp and headers if you want to send some extra metadata. The value can be whatever you want to send, for example, JSON or plain text, and it's represented as a byte array. The key for a record has a special meaning. The producer must know which partition to write to. This is not up to the broker. So before a producer can send any records, it has to request metadata from the broker about the cluster. The metadata contains information on which broker is the leader for each partition, and the producer always writes to that leader. The producer then uses the key to know which partition to write to. The default implementation is to use the hash of the key to calculate partition. You can also skip this step and specify partition yourself. A common error when producing records is setting the same key or a null key for all records, which result in all records ending up in the same partition, and you get an unbalanced topic. And then we have the consumers. There are 2 types of consumers. First, we have the low-level consumer, where you specify which topic, which partition, and also which offset to read from. The offset can be a fixed number, but you can also request to read from the beginning or end of a partition. This can be cumbersome since you have to keep track of which offset each consumer has consumed, so you don't get the same records again and again. Because of this, Kafka added another easy way of consuming, and it's the high-level consumer, more known as the consumer groups. A consumer group consists of 1 or more consumer, and you create a consumer group by adding the property group.id to a consumer. If you give the same group ID to another consumer, they will join the same group. The broker will distribute which consumer should read from which partition, and it also keeps track of which offsets the group are at for each partition. It tracks this by having all consumers committing which offsets they have handled. And every time you add or remove a consumer from a group, All the partitions is rebalanced between the group, so they have an even load. Because of this, there are some things to think about. You should make the consumer stateless, since it might get different partitions assigned to it on a rebalance. And also, all consumers in the group are paused on a rebalance. So if you have clients that times out or are restarted often, the throughput will suffer. After looking at the producer and the consumer, we will look how the broker receives and stores records coming in. So the producer sends a record to partition 1 in topic 1, and since that partition is empty, the records ends up at offset 0. The next record coming into partition 1 will end up at offset 1, and the next record will end up at offset 2, and so on. This is what is referred to as a commit log. So each message is appended to the log, and there's no way to change the existing records in the log. These offsets is also the same offset that the consumer uses to specify where to start reading. Note here is that the offsets are per partition. They are not shared across the topic. So the consumer has to know which offset it is for each partition. This is also a good way to find out if a topic is unbalanced. If some partition has much higher offset than others, it's a sign that the producer doesn't spread the records across all partitions. And now let's zoom out a bit and look at the Kafka cluster. Running a single Kafka broker is possible, but it doesn't give you all the benefits that Kafka in a cluster can give. For example, data replication. A Kafka cluster is multiple brokers replicating data between them, making sure that your data is always available and the load can be distributed amongst the brokers. Zookeeper keeps track of which brokers are in the cluster. You can have multiple zookeepers in the cluster, but it's recommended to have 3 or 5. There must be an odd number to always have a majority in a vote, but having too many just gives a lot of overhead. Adding a broker to a cluster is as easy as having a new broker connect to the same zookeeper as the cluster is using. And the same goes for removing a broker. Basically, you just stop the broker and zookeeper will mark it as gone. This also means that if a broker fails to connect to zookeeper on an interval, it might be dropped from the cluster. And now we look how replication works. So in this picture here, we have 3 topics and the color boxes represent partitions. So the blue topic on top has a replication factor of 3, which means that each partition is on every broker in the cluster. And the pink topic has a replication factor of 2, so each partition is on 2 brokers. So if you see that the blue partition here is on broker 1 and broker 2, but the red is on 1 and 3. And then we have the orange topic. It has a replication factor of 1, so each partition is only on 1 broker. So if broker number 3 goes down, you won't be able to produce or consume from the yellow partition in the orange topic, since it's only available on broker number 3. But how will other topics behave? Let's have a look. First, every partition has a leader. A partition leader is a broker that the producer is writing to and the consumers are reading from. It's up to the other brokers, known as followers, in the cluster to replicate the leader by pulling the data. So here we have broker number 1 is the leader for the first partition, and the other 2 are followers. And for partition number 2, broker number 2 is leader and the other are followers. You should strive to have a good balance of leaders. So each broker is leader of equal amount of partitions, so you can better distribute the load. And here we have broker number 3 is leader of partition number 3. And as we see here, we have a well-balanced topic. And here we have a case of broker number 3 has gone down. It can be, for example, that a broker failure, timeout to talk to zookeeper, the server is rebooted, or some other user actions on the server. The result is that partition number 3 is unreachable. The Kafka controller, which is the broker, which can be any broker in the cluster, discovers that broker number 3 is down and elects a new leader by looking at which brokers are in sync and select one of them as the new leader. If no broker are in sync, no new leader can be elected. Here you can either wait for the broker coming back up again or enable unclean leader election, which can result in data loss since the new leader might not be in sync. But here we have the case that broker number 2 gets elected as new leader for partition number 3. Now all clients must update their metadata to make sure it knows who the new leader is. When broker number 3 comes back, it might be elected as leader again for partition number 3 or any other partition. But first it has to act as follower for all partitions to catch up on any missed data. And only when it's back in sync, it can become leader again. And now it's time to do some comparison.
Yes. Some features and behaviors to compare. We first of all have some obvious things. Both Kafka and RabbitMQ are open source with different licenses. RabbitMQ has been on the market for a longer time than Kafka, but both of them are considered to be reliable and scalable messaging systems. Kafka is written in Scala, and RabbitMQ is written in Erlang. Most client languages are supported by both Kafka and RabbitMQ. Records in Kafka are pulled by the consumer, while messages are pushed to the consumer in RabbitMQ. A consumer can pull a message from RabbitMQ, but it's not always recommended. Kafka uses a custom protocol on top of TCP/IP for communication, while RabbitMQ by default implements AMQP 0.9.1. RabbitMQ also supports several standardized protocols such as AMQP 1.0, MQTT, STOMP, etc. The use of a standardized message protocol allows RabbitMQ users to replace the RabbitMQ broker with any other AMQP-based broker where Kafka can't simply be removed and replaced, since it's the only software implementing this protocol.
And here's a big difference between them. In Kafka, records aren't deleted from the broker when the consumer consumes it. It's instead persisted in the broker until a retention policy is fulfilled. The policy is either a time period. You can say that the data will be kept for example, 7 days, or it's a size limit. This is something you configure when you create a topic. And by having this feature, it allows for the consumer to replay records, either just the latest one or from way back in history.
Messages are by default stored until ACT in RabbitMQ. As mentioned, messages can also be NACT and thereby added back to the queue. It's also possible to store a message in a queue for a given value of time before it's dropped from the queue, and also to take care of messages discarded from queues.
And in Kafka, there's no operation to get records back into the topic or the partition. You can either choose not to commit the offset for that message, leaving it available to be consumed for another time, or you can republish the message back into the topic again. Routing. As Lovisa mentioned earlier, RabbitMQ supports flexible routing of messages via exchanges. Kafka doesn't have any routing built in. And this is because it's up to the producer to decide which partition to write the data to. You can create dynamic routing yourself with the help of Kafka streams, where you dynamically route records to topics, but this is not a default feature. Message priority. This is also another thing Lovisa mentioned in her intro, message priority, that we use for handling the database backups. Kafka doesn't have this feature. All records are stored in order on disk, and the consumer cannot change the ordering.
RabbitMQ supports delayed or scheduled messages through the use of a plugin. And Kafka provides no support for such features. Kafka writes messages to partitions as they arrive, where they are immediately available for consumers to consume.
Consumer scaling, meaning increasing throughput on the consumer side. And with both Kafka and RabbitMQ, you can increase throughput by adding more consumers. In Kafka, you can only have one consumer on the partition per consumer group. So if you have 10 partitions and one consumer in the group, that consumer will consume from all partitions. And if you add consumers to the group, they balance the partitions among them. But if you add more consumers than you have partitions, extra consumers will not get any records. For this to work, you need to add more partitions to the topic. One thing to consider here is, if you want all the messages in a topic to be ordered, you can only have one partition, which means only one consumer. In RabbitMQ, you can have multiple consumers on the queue. They simply take the next number of messages available in the queue. The messages will always stay ordered in the queue, but the ordering in the consumer might not be guaranteed in this case. Scaling the cluster, the brokers. Kafka can be scaled by adding more servers or bigger servers. Adding more servers will give you higher throughput since the load is better distributed. Adding bigger servers, more memory and CPU, will give you faster replay, and it's good when producers are fast, but consumers are slow, as Kafka can keep more records in memory, and it doesn't need to fetch the data from disk.
And adding more brokers or servers does not always give you better performance in RabbitMQ. We at CloudMQP scale by bumping up the resources on the machine instead. Our customers usually have a message volume that both Kafka and RabbitMQ can support without any problems at all. And most of us don't deal with the scale where RabbitMQ runs out of scope. In other words, we have not seen many cases where RabbitMQ reaches a limit per second that has been outpaced by the RabbitMQ server.
Monitoring. There's no built-in monitoring in Kafka. There are some commercial tools and quite a lot of open source monitoring solutions. Some examples are Burrow from LinkedIn to monitor consumer lag. And as you see in the picture, the Cloud Kafka Manager is for monitoring and administration, which is developed by us.
RabbitMQ has a built-in monitoring tool, and it's not much to say about that, but among other things, queues, connection, channels, exchanges, users and user permission can be handled, created, deleted, and listed in the web browser. And you can also monitor message rates and send or receive messages manually.
That's some comparison, and I will show some use cases for both Kafka and RabbitMQ. The first use case for Kafka. You operate a web shop and you would like to have this similar products feature on the site. And what you can do is that you record all actions that the customer does on your website and send all these to Kafka. Then you have a separate application that consumes this record, filtering out all those that has to do with products, and select similar products and send that back to the web shop so it can be shown on the next page view for the customer. And since data is persisted in Kafka, we can run a batch job during the night that generates an email with suggested item to buy and send that to the customer as well. Another use case, application health monitoring. Then within your company, you want all the servers to be monitored and trigger alarm if anything changes rapidly. So you can install an agent that reads the usage, for example, CPU and memory of the server, and send that to Kafka. You can also have syslog forwarding all logs to the same Kafka cluster. Then by using Kafka streams, we can join these two topics together and trigger alarm if any metric has changed over a threshold. And since we've joined the topic with logs, you can include the logs around that same time frame. The last use case, Kafka as a database. A well-used feature in Kafka, log compaction, doesn't exist in RabbitMQ. Log compaction ensures that Kafka always retains at least the last known value for each record key. Kafka simply keeps the latest version of the record and deletes the older with the same key. An example where we use log compaction is to keep the current status of each of our customer clusters. So we publish the current status of the cluster with the cluster name as the key to a topic in Kafka that is configured to have the cleanup policy set to compact. When we consume this topic, we get something like a hash map with the cluster name as the key and the latest status of each cluster as a value. And by continuing to consume this topic, we have a stream of new statuses for all clusters.
And worth mentioning for that use case is that we have a couple of thousands of clusters that we are managing.
Yes.
RabbitMQ is a simple and traditional pub/sub message broker, and it will most probably scale with your business all the way. RabbitMQ is ideal when you need to handle long-running tasks. Many of our customers let RabbitMQ queues serve as event buses, allowing web servers to respond quickly to requests instead of being forced to perform intensive tasks on the spot. An example of this is the case given in the introduction, where one service just add a create backup message to the queue, and then let the consumer handle the request once the consumer have time to handle the request. Softonic, a company working with file share, uses RabbitMQ. They let customers upload files, and these files are added to the queue for file scanning, and the file scanning service is then subscribing from the queue. We have a property listing platform as a customer that are using RabbitMQ. Once a real estate broker adds a new image to the property, an image scaling task is given to RabbitMQ. The image scaling service grabs the task from the queue, scale the selected image, and in the end, the image is ready to be shown on the website or in the app with this new size. RabbitMQ is used by many customers in between microservices, where it serves as a means of communication between applications. avoiding bottlenecks passing messages. And customers thinks it's beneficial to decouple different concerns in applications and allow communication between them asynchronously with messages. And that way, different parts of the application can evolve independently, be written in different languages, and or maintained by separated developer teams. An example use case is the company FarmBot, an open source robot farming app. And they are in many ways using RabbitMQ as a machine-to-machine chat application. CloudMQP and Cloud Kafka are built upon multiple small microservices where we use RabbitMQ as our messaging system in our own production. Our first goal was to provide RabbitMQ as a Heroku add-on, and we knew that we wanted a microservice architecture for all the common reasons like flexibility, loose coupling, and so on. So we started out with a RabbitMQ server, some Heroku API endpoints, a database to keep track of stuff, and an AWS integration, and messages like account create and account delete to a lesser extent, thankfully, started flowing through our Rabbit. And today we have support for more platforms, data centers, and lots of integrations. So RabbitMQ is simply responsible for distributing events to the services that listen for them. This is, of course, a simplified overview of our architecture today. I think that was all from us.
Yeah.
Yes.
Cool. Let's back to the questions. Okay.
It was a long time. I haven't been talking for a long time. It feels like with all this Corona.
Yeah, I agree with you. Normally, I mean, with the real people, I love that feeling when interaction. But to be honest, now it's hard for me, much more harder. So the first question, let me check because there was discussion on our chat. So the first question was about the replacement, Zookeeper, because yeah, Confluent announced that the Zookeeper will be replaced, and the question was about what will be replacement, and I already answered on that question because nothing. Kafka will store everything inside without any external software like Zookeeper. So there is a link to explanation. So maybe more. I have a question. Because I heard that in RabbitMQ there is a limit, 1 CPU per queue, because it's based on the Erlang and how it's processing the events. So can you elaborate more about it?
Yes, you also have plugins available so that you can actually make sure that queues are that the messages are spread out all over different queues on different cores. You have sharding and you have the consistent hash exchange plugin, which you can use. That will help you.
And will help me with?
With the adding messages to queues on different cores, or what did I miss in the question?
Okay. So yeah, Pavel, you can unmute yourself, okay? And ask question directly, and next one will be Ariel. Yeah, Pavel, are you there? Okay, maybe I will read. Pavel asked, what happens to messaging in Rabbit when consumer responds with NAG, so negative acknowledge? Is message returned to the queue or back of queue?
It should be returned to the beginning of the queue.
But I know there is ordering, I would say, so you can set the priority. So is it? I mean, this message will be RabbitMQ give her highest priority or at the end of the queue?
Do you mean the next message, or do you mean messages when you are using just priority queues?
Negative message. I mean, negative acknowledgement.
Negative acknowledgement in a priority queue. I'm not. I'm not sure about that.
No.
I can't answer that question.
Okay, Ariel.
I would say if it's
yes,
back of the queue, and then all the rules apply again, so it still has high priority. It will go first in the queue. If it's a normal queue without prioritization, it just stays in the back of the queue. I think all the rules are applied again.
Okay, Ariel, are you there?
yeah.
Yeah, so maybe now, because we've heard some strange noises.
Yeah, so I was just asking what the benefits of some of the other layered architectures like Infobus provide over using MQ or Kafka directly.
That's a good question. I can't answer it because I haven't used ECQ or mass transit or first one, service bus.
And service bus, right?
Are they based on AMQP as well, or do they have other protocol?
I mean, generally they are using queuing in order to do sort of like remote procedure calls where the message embodies a request for a particular method to be invoked and get a service done. But I mean, I just don't know precisely what additional services they provide over the native services of a queuing technology.
I can't answer that either. But we can have a look at another popular comparison is RabbitMQ versus simple queue service from AWS, because if you just look at it quickly, they look the same. Publish a message and then someone else consumes the message and you have a queue between it. The main difference here is RabbitMQ has a lot more features. It has a lot more exchange types that Louisa talked about. So you can customize the usage. So it's easier to scale out. So if you have more and more requirements on where to send the data, it's easier to scale out. Simple queue service is, as the name says, simple. But I haven't looked at the other ones.
Okay, fair enough. Thank you very much.
Even though if we would have looked at it, it's hard to give a fair comparison since we are working daily with Kafka and RabbitMQ.
Well, I mean, they actually ride on top of, like, for example, N-Service Bus will either use MSMQ or RabbitMQ or SQL Server as its queuing mechanism, as its transport layer. But the question is, what are the features that these info buses are providing that one couldn't do directly? I guess perhaps they're just abstracting away a little bit, making it easier, but they're ultimately using the underlying queue technology as their transport mechanism. They're not replacing it, they're augmenting it.
Okay, yeah, so they add some more specific use cases for it.
I guess, but I appreciate the candor. Thank you very much.
Okay.
Okay, the next one, Łukasz Leszewski. You can unmute yourself.
No, it was general assumption that Kafka, regarding Kafka and RabbitMQ. So Kafka scales horizontally and stores data according to the data policy. And the RabbitMQ is just for asynchronous async communication between services. Is that a good conclusion from the meeting?
Yeah, it's a very it's a very good. What's it say? No, but you're correct. Yes.
Thank you.
Also, from my point, I will add that the difference between Kafka and the RabbitMQ. In Kafka, usually there is a push mode. Of course, there is some options to change it, but usually that broker sends the messages to the consumer, and there is special option to change it how much you send them. In Kafka, it's only pull. Right, there is no option that the broker is sending something. It's the consumer is connecting to the Kafka broker and collecting the messages. So that's the main reason. Also, times to times the difference is the people call the Kafka like the dumb broker and the RabbitMQ like the smart broker, because in Kafka there is no at all logic inside. I mean, you can, like Lovisa and Magnus showed, you can choose which message. It's going to which one queue. There is no option like that. You just starting from the producer, sending to the proper topic, and that's out. But that's all. But on RabbitMQ, you have logic inside. Like one of the slide was about it, so you can like copy this message to 2 or 3 different or even more queues. And from the other side, in Kafka, you can consume the same message many times. In RabbitMQ, only once from the one queue. So if you would like to consume the same message a few times, you need to copy it and store in the different queues.
Yep.
Yeah, and Evgenia, sorry if I pronounce your name wrong.
Yes, you can call me Jane.
Hey Jane.
Yes, so I was a little bit late, but I just would like to ask you about metrics that should be monitored for Kafka, because right now we are monitoring mostly the log. Maybe do you have some other recommendations about what we should also consider by monitoring Kafka?
And it's a good question. It depends on what you are looking for. Consumer lag, you can see if your consumers are slow or fast, basically, if they can keep up with the producers. So that's if you can categorize it client metric. It's still on the broker, but it's based on, it shows how well your consumers are doing. Most of the metrics that we use are broker specific. For example, how long each produce request takes. But then you can see, and also how long each request between each broker for the data replication, how long that takes. And also on the consumer side, you can see how long. So basically looking up how long the request takes. And there you can see if you do any changes to the hardware underneath. If these metrics go up or down, then you know you made a good change. That's one. Another thing to monitoring is under-replicated partitions. That will show you how many partitions that are not in sync. For example, if one broker is having issues, for example, it has too many produce requests, so it's busy with catching up on the other partitions, so it will lag behind, and that will show up as under-replicated partitions. Was that a good answer? I see that someone mentioned here Datadog. Datadog has a dashboard built for Kafka. So if you enable their agent on your brokers, you can